Right, everybody? It is 1 o'clock and time to start because we're going to talk today about something that has relevance to every single person in this room. Even if you've been sat there patiently talking about Ekman spirals thinking, I'm never going to use this ever again in my life, which I know some of you do. Remember, this is what is happening now. This is something that we are going to have to deal with. We are already dealing with, and we are going to have to continue dealing with over our lifetime. And we're pretty lucky. We're pretty rich. We're in a developed country which can deal with a lot of these changes, but that isn't necessarily the case everywhere. And so it's a really important topic. So even if you forget everything else that you ever did in system science classes, I really hope that this week in particular and this lecture on Fridays sticks with you. Because it is something that I feel everyone should be aware of. Okay, so this is the stuff I showed you on Monday. I wanted to ask if there were any questions, first of all, about any of that stuff. And if not, I have had enough questions that I was kind enough, because I'm lovely, to bring you an example, okay? This is the one I've been showing people from my in office hours, okay? And it's enormous. Yours does not need to be this big. But given that it is enormous, it is easier for you guys to see. And I like this one, okay? It looks like a mess, okay? And that's because it will look like a mess. The Earth system is very complicated and it's interrelated. What I like about this particular example is that it has those 4 spheres on it. It's not massively subdivided into separate things. It doesn't need to be. It gets really complicated. I'm sure you're finding this if you try and include everything. But what she has got on here are all of those really important links between those spheres. So she even has things like the fact that we have an outer core generates a magnetic field, and that allows us to retain our atmosphere. That's a really good geosphere-atmosphere link. Things like evaporation. She's got the biogeochemical cycles in here. Things like nitrogen fixation. Carbon going into weathering into sediments, okay? So she's got really all of the things on there that I want. This is perfect. This is sort of 50 out of 50 points, okay? And so if you can produce something like that, that's great. Yeah?
2 questions. Online, you had examples where it was divided into subsections.
Mm-hmm.
So on this one, only a couple of subsections appeared. Is that how?
Yep, you don't actually need subsections as long as you have the spheres. The subsections actually help. I think especially for the hydrosphere, because you can imagine that the processes that affect groundwater are vastly different from the processes that affect the oceans. So wind has a strong influence on ocean circulation, doesn't affect groundwater really at all. So
hard time finding ones where like things could fit into like 3 sections where everything could fit.
Yeah, so this is fine, okay?
How many do you want? How many connections are there?
So there isn't a number of connections, and why I say that, because people will get those like 20 or something and then they will give up. This is a challenge for you guys. It's not a fill in the blank, a circle the correct answer. There are enormous amounts of processes out there, and how you sort of group them or how you sort of individually put them is sort of up to you. And so it's one of those things where once you start doing it, it'll be really easy actually to find enormous numbers of connections. So just keep going. See it as a challenge. The idea behind this isn't just to torture you because I like being mean and making you work. The idea is that it is a really good way of making you study as well, because by now you've read through the slides again and again. This actually allows you to go back and look at your notes in a different way. You're looking at it in terms of how I want you to look at it, looking for those connections between the system, because after all, this is an introduction to the Earth system. It's not an introduction to the ocean's atmosphere, biosphere. We're looking at the Earth as a system, okay? So hopefully that helps clear up a few things for some of the questions, okay? Final exam, just a reminder, it is happening, all of the information is there. You are allowed a one-sided page of notes, a normal size page, and it should be one-sided, okay? There's only notes on one side. The final review session, I'm holding that from 7 till 8 on Monday, and I'm sorry that it's late yet again, but that's the only time we could get a room that would hold enough people. Does anyone have questions about the final? No? Okay, great. In that case, let us talk more about what is happening with our climate. So this is what we talked about on Monday. We talked about the fact that Weather is just what the atmosphere is doing at one particular time, and we've talked about that already. But this is our climate system, and it's actually very, very complex. So yes, it involves the atmosphere and the temperature and windiness and cloudiness and everything else, but it also involves things like that ocean circulation. It involves changes to the biosphere, changes to Earth's albedo, changes in the hydrosphere to do with things like ice cover. All of these things come into play when we talk about our climate system. And of course, our climate system is powered 99.9% by energy coming from the sun. Okay? That other tiny percentage is what's sort of escaping as geothermal energy from the Earth, but the vast majority of it is coming from the sun, and that what happens to that energy is what affects our Earth's temperature and climate. Okay, so let's launch straight in. So we talked about a number of different reasons that climates can change. Which of these shows something that is not a reason that our climate is changing and that climates change in general? Any more votes? Right, let's take a look and see. Okay, well, let's talk about what some of these things are. What does C show? Sunspots. Okay, does that help you out a bit? What does B show? A very large volcanic eruption. This was Mount Pinatubo in 1991, I think it was. So you're probably too young for that. What is A showing us? Orbit. Orbital changes. This actually shows that eccentricity cycle, remember? And what does D show us? The ozone hole. So I heard an O from the center of the audience there. So if I ask the question again, let's see if we can get a better answer for what was going on there. Think back to your quiz. Any last answers? Right, let's see if we get a better spread this time round. That's better. Okay, thank you. So yes, do you remember when we talked about how humans are affecting the Earth, we talked about a number of different ways that we're messing things up. But one of those ways was we had released CFCs that had destroyed an awful lot of ozone and had generated an ozone hole. But remember, I made the point that, remember, ozone blocks incoming ultraviolet light. It's not anything to do with our greenhouse effect, which is where we have incoming visible radiation that comes straight through the atmosphere, is absorbed by the Earth, and that energy is re-emitted as infrared, which does get absorbed by greenhouse gases. Okay? So remember, ozone is nothing to do with the greenhouse effect. So here were our 7 factors that affected our climate and that could cause it to change. So we had things like variations in solar output. We had distribution of continents, mountains, ocean basins around the world, surface characteristics, in other words, albedo. Do we have big areas of ice? Do we have surface deforestation? Do we have changes in greenhouse gas concentrations? And we're going to talk today a lot about carbon dioxide, but we're also going to look at things like methane, which is a really powerful greenhouse gas, and also nitrous oxide, which is one we haven't mentioned as much, but is another one that's contributing to change today. Aerosols, remember they can have quite complex effects, because some of them can act to reflect back incoming sunlight and so cool us down. Some of them actually trap more of that outgoing radiation and so warm us up. So that's a bit more of a challenge. Changes in Earth's orbit are Milankovitch cycles. So we had our eccentricity, which was whether our orbit is elliptical or more circular. We had, let me think now, obliquity, which is how far tilted over we are, so whether we're 21.5 or 24.5 degrees tilted. And then we had precession, which was where on our elliptical orbit are we tilted at any particular time. And then, of course, we said that those Milankovitch cycles were so exciting for us because they could finally explain the timing of our glaciations that we've seen in the last 2 million years, how they seem to happen every 100,000 years or every 40,000 years. But remember that they can explain the timing, they can't explain the magnitude of the climate changes we see. In reality, there are these feedback processes that kick in that sort of amplify those changes. Okay? So these were all of the things that we talked about on Monday. And this was sort of where we got to. We sort of did like a 5-minute tour of the climate of the last 100 million years. The sort of 5-second version is it used to be a lot hotter, now it's a lot colder. And we've had these wiggles every 100,000 years in our temperature in the last sort of 2 million years. And in particular, the last 10,000 years, we're in a nice warm interglacial. There's still ice around on our planet, but there's less around than previously. And our temperature, that red line for that last 10,000 years there, the bit that's sort of highlighted in the bracket, has been really amazingly stable. Especially if you say compare it to that last sort of few 100,000 years where we've seen enormous swings in temperature backwards and forwards. And that stability is arguably what has helped us be able to create things like agriculture, because it's allowed our climate to be stable enough for that to happen. So that's a really interesting story about how climate might interact with human civilization. But today, we are really drastically changing the pattern that we've been seeing for the last, arguably 2 million years, but most definitely the last 800,000 years, where we see this nice sort of 100,000 year cycle where CO2 and temperature rise to interglacials and then fall into sort of cold glacials and rise again. And in particular, this is our Keeling curve, our CO2 measurements that we've been taking every month faithfully from sort of the 1960s onwards. And you can see that we're really dramatically changing what's in our atmosphere. So, I want to know what you think. I want to see whether what we're going to cover today actually does change anyone's mind, or whether you're actually convinced already. Okay, so is our climate changing? Yes, no? You have 15 seconds to tell me. Shouldn't be a difficult decision. Okay, a couple more seconds for people to find their iClicker. I think that's everyone, so let's take a look. So 93% say yes, 7% say no. Okay, we'll see what happens to that number. My more complex question is, how much of the change that we're seeing is due to human activities? Is it 0 to 10, 10 to 50, or over 50%? What do you think? What does your background knowledge tell you? Okay, we'll take a look and see what our ratio is this time around. So we have a more or less even split between 10 to 50 and over 50%. Okay, and these are the two big questions that we're going to be looking at today. So I'm going to ask you this again at the end, and we're going to see if anyone has changed their mind or changed their opinion. Okay. So, our questions today are, how has our climate been changing, and why is our climate changing? So first of all, I need to introduce you to the Intergovernmental Panel on Climate Change, or the IPCC for short, because that's way too long a name. So So this is sort of more or less, I think Starrell described it just before in her office as the Bible for climate change people, and I don't like introducing religion to climate change. But this is really the point where the place you should go. Do you need anything for a writing class, for an economics class, for anything? This is where you should go for anything to do with climate change. Because this report involves an enormous number of scientists. It's openly peer-reviewed, so anyone in the world with access to the internet can comment on it. And every sort of 6 or 7 years, they release a report that summarizes everything that we know about climate change and produces the statistics that you see and the information that we know. And the, I think, amazing thing about these reports is that everything in these reports has to be agreed on by every single one of the 120 participating countries. And you can imagine what a challenge that is, right? Because everyone will argue over this or that sentence. Everyone has their own sort of motives for wanting certain things included or not included. And so this is really what is accepted by the world scientific community, by the world's governments, and really is sort of, for that reason, a pretty conservative document. It doesn't make wild speculation because it can't back it up, and people wouldn't accept that in this sort of report, okay? And in fact, anything that has been included in the most recent one in 2013, 2014, had to actually have been published about 1 or 2 years ago now, because there has to be time for people to read that and sort of come back and comment on whether that's actually reliable research or not. So only really reliable research goes into it. And this is what my challenge is, because I have to cover what's in these reports in 3 lectures. And in fact, I can't even come close, because, these are the reports from 2001. This is the 3rd one. We had another set of 4 reports in 2007, and this is what's in the process of coming out right now. Do you remember I was massively overexcited in the first lecture because that morning we just had the sort of final agreement from those 120 countries for the physical science basis. This is all about just the science, okay? So this is all the science that we know about climate change. This is what we know about the impacts, the adaptation, the mitigation. That's how we could approach those. Oh, sorry, this one is mitigation. This is mitigation, okay? So you can see there's enormous amounts of material, and I have to summarize it in sort of a few slides, okay? So this is the place to go if you ever want information, because there's enormous amounts out there, and that's where the reliable stuff is, because there's an awful lot of misinformation about this topic as well, as we will see. Okay, so, and it's not worth making the point that yes, I'm most interested in the cool sciencey bit, but your interests as an economist, as a psychologist, as a biologist, as an engineer, all of those things come into play. This is not just an earth science problem. We can say there's a problem, but we're not necessarily going to be the ones that go about fixing that problem. That really does rely on politicians and other people around the world. And so it's worth thinking, where do your particular interests fit into this sort of document, and sort of where do you play a role? And all of these documents are written in horrible sort of legal type, sort of sciencey language, so they're pretty dense. They're not sort of bedtime reading. But that does mean that we sort of have a certain amount of certainty quoted with each of these things. So if we say that the temperature has risen by this amount, there'll be uncertainty associated with that and quoted with that. And things that you might read when you're sort of flicking through this document are things like, we are virtually certain. That means we're over 99% confident that this is something that is true. Extremely likely is sort of greater than 95. Very likely over 90, likely is greater than 66. All of these things we can quantify how certain we are about the various things. So if you're interested, I wouldn't suggest perhaps reading the whole thing, but there's like a little summary for policymakers that's maybe 30 pages or so, and you can have a look at that. Okay, so let's take a look at some of that information, and I had to spend a lot of time yesterday updating my slides because we have the new physical science, at least in draft form, available on the internet, and so we have the updated, most recent information available now. And so for our atmosphere, let's deal just with the atmosphere to begin with. We have seen warming. We have seen a warming of 0.86 degrees Celsius from 1880 to 2012. And that's what's shown in the graph on the right here. You can see, and you can see where the figures are from as well. So from 1850 up to 2012 or so, you can see that our temperature has been rising. And we plot it in a funny way sometimes. We sort of take a sort of an average, and then we plot whether it's less than that or more than that. So that's sort of our anomaly almost. But you can see that overall our temperature has been rising. And if we plot that as decadal averages, so 10-year averages, you can see it really clearly that especially most recently we've been increasing a lot. Because there's been a lot in the media about our slowdown in warming. And they are right that actually in terms of our atmospheric temperature, we haven't seen sort of continued growth in the last sort of 5 years or so. But remember that we're always going to have noise on top of that overall warming trend, so that's not particularly surprising. You can find plenty of other times, plenty of other decades in that record where it might look like a straight line or that it's even cooling down. But overall, that trend is increasing. And that energy isn't going into the atmosphere. Where it's actually probably going, we think, is into the oceans. That's why our atmosphere may not be as warming as much as we thought it was. Okay? And the fact is that we're likely hotter today. So remember, likely is not as much as virtually certain, but we're likely hotter today than any time in the last 1,300 years. So we have made quite an impact. And that warming isn't distributed evenly. That's something that people sometimes get surprised by. This is that observed change in surface temperature, this time from 1901 to 2012. And where you see white areas are where we just don't have enough data to say anything with confidence. But you can see that there's certain patterns. We warm more over land than over the ocean. And that probably makes sense with what we know about heat capacity and everything else. And you can also see that we've been warming more at higher latitudes. And here's where our positive feedbacks are kicking in. Things like that albedo effect is increasing the warming in sort of high latitudes. Okay? So you can see that in parts of maybe Canada, Alaska, in parts of Asia, then we've seen maybe over 2 degrees Celsius of warming, more than that, 0.8. Okay, so now let's look at the oceans. So unsurprisingly, if the atmospheres have been warming, the oceans have also been warming. And you can see again our temperature anomaly. And this is the sea surface, okay? But actually, if we look at our records, and we have fewer and fewer as we go deeper because it's harder to do, but if we look, we can actually even see slight warming now below 3,000 meters in some parts of our world ocean. That's 3 kilometers down, we can see a warming. A very, very slight one, but still, to me, that's just astounding, okay? And that's because our oceans, do you remember how important our oceans are in terms of how much energy they can store? Our oceans have actually taken up about 90% of that extra energy that's in our atmosphere due to things like increased greenhouse gases. So yes, we've seen an increase in our atmospheric temperature, but the amount of energy that's stored in our oceans has also been very rapidly increasing. Okay? And related to that, therefore, we have an increase in sea level. So I think I asked this again in our very first lecture, what's the main reason that sea level has been rising? And I think I caught out most people on this one. It's not necessarily that glaciers are melting. That's certainly part of it and an increasing part of our sea level rise. But actually, a big component of the fact that our sea levels are rising is just that the oceans are getting warmer. If you warm up 4 kilometers of ocean, then you are going to see that it expands a little bit, and that is going to be reflected in the sea level. So on the top graph there, you can see the sea level change from 1900 to 2010 or so. We've seen maybe a 10 centimeter rise. That sounds like nothing. I know that you're all not metric, but that's like that much maybe. Okay? And it doesn't sound like a lot. But it's substantial. That's in 100 years. Imagine if in another couple of 100 years what that could become. And also related to the oceans, do you remember we talked about ocean acidification and the fact that as we put more CO2 in our atmosphere, what happens is more of that CO2 dissolves in our ocean, and that actually makes our ocean water more acidic, and that's going to cause problems for a lot of our ocean life. And here you can see that our green line here shows the change in ocean pH. It's gone from sort of 8.12 or something to 8.06. And that sounds like nothing at all, but remember that this is a logarithmic scale. So that's like a 25% or so increase in the number of hydrogen ions. So that's pretty substantial. Again, it's not going to take much more than that for us to see substantial difficulty. Okay? The cryosphere, our ice, what I'm going to spend 10 weeks on next quarter. It's going to be fun. Our ice has been changing very, very dramatically, and we can see that visually from sort of photo sequences such as that one on the right, but also things like from satellite observations of sea ice, paired with sort of further sort of documentary records. So here's our sea ice concentration, and you can see it was quite happily plodding along until maybe 1960, 1970, and we've seen very, very dramatic loss in terms of the sea ice sort of extent in the summer. We've maybe lost half of it now in the summer, and that is a very great concern. Okay? It's not just that, we're losing permafrost, we're losing snow cover, and we're losing sort of ice sheets. Okay. Precipitation, rainfall, this is actually a much more challenging thing to model. This is something that we still have a long way to go. And so you can see, compared to that color map that I showed you of the surface changes in temperature, there's a lot of white on this map. And where that white is, we really can't say what will happen or what has been happening. But you can see that from the 1950s to 2010, those blue areas are areas that are wetter than they were in the past, and those red areas are drier. And so you can see certain parts of the world, so North and South America, the eastern sides at least, the northern parts of Europe are getting wetter. And that's great, but they were already quite wet. The dry parts of the world, such as the Mediterranean, around the Sahara Desert, the Sahel region in Africa, parts of Australia are all getting drier. So our dry parts are getting drier as well. Okay? And we're also seeing more frequent episodes of floods and droughts. So, is our climate changing? 15 seconds. Okay, I think that's everyone. So 9% of people that disagree with me, well, I'm afraid you're wrong, okay? I know that climate change is one of those things where we're all very careful about it. I'm absolutely going to allow you an opinion on what we should do about it. You're not allowed an opinion on this. This is something that is happening. There is no disagreement about this. This is as true as anything that we talked about in terms of Ekman's spiral, thermine, haline circulation. You can read those graphs, then the climate is changing. It is changing, okay? So in this case, the answer is definitely yes. The climate is changing. So let's think now about why that's the case, okay? And so just before I did that, I wanted to show you, given that response. So here is that fifth annual report from the physical science basis. And if you scoot down to page sort of this one, this is observed changes in the climate system. And this is the fundamental bottom line. Warming of the climate system is unequivocal, okay? And since the 1950s, many of the observed changes are unprecedented over decades to millennia, so thousands of years, okay? The atmosphere and ocean have warmed, amounts of snow and ice have diminished, sea level has risen, and concentration of greenhouse gases has increased. So there's no real arguing about that. Everyone around the world will agree, okay? But what we want to look at now is really why that's happening, because that's really what we need to know, because we need to understand what aspects of our behavior we perhaps need to address, okay? So, of my list of 7, I reckon there's 2 that we don't really need to think about if we're going to think about climate over maybe 100 years or so. Which of these do you think I can rule out if we're only going to consider climate for the next 100 years? Sorry? Milankovitch cycles, yeah. So remember, our cycles were maybe 20,000 years, the shortest one, 100,000 years for the longest one. So really, in the next 100 years, we're not going to see significant enough effects to really bother thinking about Milankovitch cycles. So we can rule that one out. Which is the other one we can really rule out? Distribution of continents. Our continents don't zip around in 100 years. You can be pretty certain if you come back in 100 years' time, we're going to see exactly the same configuration of continents and ocean basins. Okay, so definitely we can rule out those two. But really, if we're going to try and look at our climate, we need to think about all of these other ones. Okay, and so I've highlighted a couple of the main ones here. So first of all, don't tell me what I want to hear. Tell me what this graph would show. So what does this graph suggest to you? Okay, let's take a look. I think I've got most answers now. So most people say B, and that's because you're telling me what I want to hear, okay? Because what actually does this show? This graph actually shows that the temperature and solar have actually seemed to match, at least over the period shown, right? So if you had just shown this graph and asked to interpret it, then I would probably have gone with C, that most climate over the past changes over the past century are due to solar activity. And that's because the people that drew that graph want you to think that, okay? Has anyone seen that graph before? No? Good, because it is taken from a documentary called The Great Global Warming Swindle. And it's been shown in lots of countries and has resulted in lots of complaints about the media. Because actually, if we look at the data, then yes, that was maybe the case up to maybe 1980 or so, but look at what's happened after that. And they didn't choose to show that, funnily enough, in the Great Global Warming Swindle documentary that was shown in 2000 and something or other. They are quite happy to cut off that data at 1980, okay? So in reality, yes, solar is really important for the Earth. It's providing most of the energy for our climate system. And you can see that even for the earlier part of this century, we can see some sort of correlation, if not quite as perfect as that graph, but some sort of correlation between the amount of solar irradiance and temperature that makes a certain amount of sense. But what we can see is that in the last 30 years especially, everyone who put B was correct, because we can see that our temperature has increased by quite a lot, whereas our solar irradiance has actually been decreasing. We can really see a huge divergence in our records there. And so why do I include this at all? It's a cautionary tale, okay? And this is what I meant when there's a lot of bad information out there. You are all very intelligent, educated people, and it is healthy to be skeptical. It is a good thing to be skeptical and think about where that information is coming from. And so when you read from a website or when you watch something called The Great Global Warming Swindle, then you have to think about whether there is a bias, whether there is a motive behind some of that material. And it tends to be much more sensible to get your information from things like government reports, from educational websites, and that's true of any scientific issue. That's really very true, okay? So that's my cautionary tale, be a healthy skeptic. So I've just showed you that we can definitely see that solar activity has a certain amount to do with climate changing, but really in the last 30 years it can't explain what has been happening. And so what else has been changing substantially in the last 30 years? We come back to greenhouse gases, where we knew we were going to end up. And here's our ice core record again, this time going back to 600,000 years ago, and then 0 is today. And this shows more than just the CO2, which as I showed you last Monday. So this again, you can see, is more or less a measure of temperature. So the black line, when it's higher, it's warmer. When it's lower, it's cooler. And then we also can see other gases now on here. So CO2 is that other black line in the middle, and you can see it rising and falling in pace with those temperatures. And that red line shows you how it's been increasing most recently. But we also have these other greenhouse gases, so things like methane. And our methane is there in our blue line, and it wobbles along and it moves up and down to a certain extent with the temperature record. But then look what happens to it. We have enormous amounts of methane compared to what we used to have. And the same is true, but less dramatically, for nitrous oxide. We also have more nitrous oxide in our atmosphere than we used to. So it's not just a story about CO2. CO2 is one of the most important ones because it's there in the biggest concentrations, but also there are other gases that come into play. And this is a horribly confusing looking diagram. So focus with me for a couple of minutes, and I'll show you an easier version. This is sort of the updated figure from this sort of new summary report that came out earlier this quarter, okay? And there's a lot on here, but let's talk through it. So you can see up the side, there's one column, and that says anthropogenic, which is sort of human-induced, and then we have natural down here. And then we have, up at the top there, we have a whole bunch of different greenhouse gases, so CO2, carbon dioxide, methane, CH4, halocarbons, don't worry too much about those, nitrous oxide. And then we have other things down there, other sort of types of nitrous oxides. But also I want you to look at aerosols in particular, which is that sort of third box down and goes across. And then we also have things like albedo changes due to land use. And then in our natural column, we have that change in solar irradiance, so how much our solar cycle has been changing. And then this line here, this 0, is radiative forcing. So basically, anything on this side of the line, we're adding extra energy to the Earth, to the surface of the Earth. Anything on this side of that line, we're actually sort of removing energy from the Earth system. Okay? So anything on this side basically has a warming effect. Anything on this side has a cooling effect. So what would have a cooling effect? If you look up that column, what things tend to have cooling effects? Aerosols, absolutely. So you can see the aerosols there, that sort of colored column is on this side. Okay? So all of these are what we call drivers of climate change. They are the things that we are changing or that are changing naturally that can result in either adding energy to the Earth or taking it away. And you can see there that that black dot and then those lines either side are our uncertainties. So my next IPCC question for you, so I'm going to skip forward and then move back. So which of those climate drivers, so carbon dioxide, solar irradiance, albedo, or aerosols, has the largest uncertainty, has the largest error bars associated with it? Okay? So which of those four, carbon dioxide, solar irradiance, albedo, or aerosols, has the largest uncertainty? Has everyone got that? Let me go back. Okay. So have a look, and then I'll flick forward again and ask the question. Okay, has everyone decided? Okay, I'm going to flick forward again and ask the question. So which of these are we least certain about? Okay, a few more seconds. Right. Yep, D. I would agree D are aerosols. Okay? If we look back at that diagram, you look up at our sort of carbon dioxide, yes, that column, that colored in brown column is quite large, but that's actually the size of the forcing it has. The error bar associated with that, that's the black bracket either side of that, isn't as large as if we maybe look down at these aerosols, especially things like cloud adjustments due to aerosols. Then in that case, those black lines, that sort of black bar, is actually really much, much larger. Okay? So those error bars are how certain we are about these things. And you can see that for aerosols, in some cases, we don't even know whether it's going to be cooling us down or warming us up. Again, because of those complex interactions. But for things like those greenhouse gases, we're really pretty certain about the physics and chemistry behind those. And so we have an awful lot of confidence in our estimates of how much warming that those will provide to the Earth system. And so down here, there's one last thing I wanted to show you, which is this is the, sort of the total anthropogenic radiative forcing. So basically, how much we as humans are changing the Earth system. And you can see that in 1950, we were maybe adding sort of half a watt for every meter squared of the Earth's surface. In 1980, we were maybe adding 1.25. In 2011, we were adding maybe almost 2.5 watts per meter squared. So this is, yes, a cumulative sort of effect that we have been accumulating energy ever since those greenhouse gases have been increasing, but also we're accelerating because that greenhouse gas sort of levels in our atmosphere have been increasing. We're accelerating the rate at which we're trapping that extra energy and warming the Earth, and so that acceleration is what could catch us out. A slightly nicer diagram than that is the one that they had from the fourth report. I think this is a lot easier to read, and so this is the one that if you want to study from, sort of have a look at, okay? This is also taken from the fourth report, because this is what they did to it in the fifth report, okay? Not needed, okay? This sort of tells us the bottom line, which is that whichever continent we look at, whether we look at land or whether we look at ocean, we cannot explain the temperatures that we see, which is that black line there. That is the average temperature. We cannot explain those average temperatures if we just use natural forcings, things like natural variability, volcanic eruptions. If we run our models with only those natural forcings, we get our sort of that blue sort of area there. That's what our temperature should be doing. If we add in those human effects, the sort of greenhouse gases, things like changes in albedo, aerosols, then we get the pink line, or the pink area there. And you can see that our record, our instrumental record of that actual sort of temperature measurement is actually following that sort of pink area as well. We can only explain what we're seeing if we include this sort of anthropogenic type forcing, okay? So that's just to show that it's still the same when they've updated it, but it's just a lot more, okay? So how much of our activities are actually, or how much of that warming, whoops, wrong thing, is actually due to human activities? So do you remember when we looked at that big table of information, what on there was actually a natural source? It was solar variability. And how much of an effect was that having on the Earth system? What actually was the main thing on there that was causing this warming? Okay, let's take a look. No one changes their mind. Okay, so, oh well, never mind. Over half, okay? It is very clear if we go back. I'm not going to let you get away with this. If we go back, on here, the natural forcings is that last tiny little box here, which is changes in solar irradiance. And that's how much change in our climate might be expected as a result of that, okay? All of those other things on there are human influences on the climate system. And so that is what is generating our enormous changes here. So it is extremely likely that over 50% of the changes that we're seeing in our climate are due to us, and likely more than that as well, okay? So Last eye clicker of the day, because I know how much you love them. Which of these things will have the largest greenhouse warming effect? Burning 1 ton of coal, the methane emitted by 1 dairy cow in 1 year, or the nitrous oxide emissions due to fertilizing 16 acres of farmland? You can ask your neighbor. It's probably going to be a guess at this point, though. Okay, I'm going to cut you off and tell you the answer. So let's take a look and see if we have consensus or not. So we have a pretty even split. And for once, that's absolutely fine because they all have the same effect on our climate system. Okay, so on Friday, we'll talk more about our future changes.